Hello, everyone. So I will start with this disclaimer. So I want to tell you that all that work doesn't have anything to do with my job. It's my private time and private research. Okay, about me. So I came here from Poland, Hacking Paris. It's my first time on this conference. I worked 15 years in IT. For 10 years, it was mainly networking. So I was a network analyst, engineer, administrator. Since last 5 years, I work as a red teamer. So I switched from networking to the security. And we'll be talking about some ways to get man in the middle or lady in the middle. So one way of getting this position is to alter the routing table. And we'll focus on that. How many of you know ICMP? Okay. How many of you know more than ICMP echo request and reply, so ping? Okay, well, that's a lot. So this protocol was first defined in 1981. And this protocol serves the role of informing systems that are communicating over IP protocol about errors in communication, mainly. So I noted here that this is a layer 3 protocol, but it also uses IP protocol as the transport protocol. So that's why the star. And how it works is like one example of ICMP error message may be from UDP port unreachable. So when the packet reaches the destination and there is some error, the host or typically the router, but sometimes just the destination host, will send back an error message with IP header of its own, and then it will embed ICMP message, which then embeds another IP header of the originating packet. So in this slide, you only see the ICMP portion, so you don't see the original IP header used for transport. And the typical, like in purple, you see ICMP header, which always has a type and code, checksum, and some for different purposes, depending on the ICMP type of a message. Then the yellow and the blue, it's the part of the IP packet that caused the error. And that will be important. And then this is just a part of our RFC, so how the source host know why it got this ICMP message. And this is very vague, it's not very specific, so the RFC for any type of ICMP message only says that the 64 bits of datagram and IP header is used to match it to the originating process. And do you know what the Type5 Code1 is? So this ICMP message is just ICMP redirect, and it was useful maybe in 80s or early 90s when we are all worried about our network speed, and we used modems, and the speed was really a bottleneck. So we wanted to have really like a shortest path to our destination. So sometimes it could happen that on one subnet, and the switch here, it depicts one subnet, so like /24, and all the three devices connected directly, so this laptop, our user, and two routers are on the same subnet. And imagine that you are, as a user, you're sending the packet to your default gateway, which is this green router. And then this green router checks its routing table. So the packets should go to the black server. And it just see that in order to route this packet properly, it has to go through this blue router, right? So it sends the packets to blue router, but at the same time, the green router will send ICMP redirect message to the host so that the host knows that it just can skip green router all along because it's not needed. It can just send the message directly to the blue router. So the communication from now on looks like this. And that's what this ICMP redirect packet do. And some really creative people thought that we could maybe just abuse that functionality. So they thought that, how about we just send ICMP redirect message to the user, claiming that we are this blue router. So in this scenario, the blue router would be the default gateway to reach this black server. So we just claim that we are this blue router, like the attacker claims that, send the ICMP redirects, and the user OS happily installs the new route into the routing table. And right now, we can be easily just man in the middle. In this case scenario, it's just one way. So traffic that goes from the user to the server is going through the attacker host. And the traffic back, if the attacker won't do any modification, will get through normal way. So attacker would just see half of the traffic. But sometimes it's just all you need, because when user sends their credentials, it goes in a packet from the user to the server, right? So did any of you ever use this attack in your pen test or red team engagements? Great. So does it still work for you? No, it stopped working. So I've noticed this stopped working. And I tried to find out what happened and why. So as you can see, it was working up to Windows XP. For macOS, I didn't test this, but I found the article and the CVE here that changed the default configuration of macOS. And right now, if you're running OS newer than Yosemite, the attack won't work at all because they just by default disable IP redirects. And for Linux, it was working up to the kernel 2.6.38. And in the bottom, you see just one command you could use to perform this attack. So what happened? So I started to looking into various Linux kernels, and I started testing this. So started from some 2.4, 2.6, 3.0, and like 10 different kernels. And finally, I found that the changes happen in 2.6 kernel. Here you have 3.6 because in 3.6 it got even more difficult. So what they changed? They are now checking if the attacker, when it sends this ICMP redirect packet, or the real gateway, when it sends this IP redirect packet, Linux kernel will check if the source IP address of this redirect packet is the same as default gateway, or gateway to reach the destination we have in mind. So it can't just be any redirect packet. We have to know what the default gateway for that particular destination is. They started using FIB, so forwarding information base, instead of routing table. So this was done for performance reasons, but it also caused that it has to go through the proper network interface. So if you have a multi-home machine, it won't work to send this ICMP redirect packet through the different interface than the one that it should be proper for this communication. And I think the most important difference was that previously all ICMP redirect packets were handled by ICMP module in Linux kernel. And right now, this module will deliver the ICMP redirect packet and hand it over to respective higher level protocol modules. So TCP, UDP, STCP, whatever, like 4-layer level protocols. So I was digging into the kernel source, so I can just show you what were the changes. The first yellow mark is just checking if this is the old gateway IP address. The other just shows that now this is a fib lookup. And then on the TCP module example, that they moved the ICMP redirect from ICMP to TCP or UDP or respective modules. So now we know all that stuff. We have to think what to do next. So just to show you again the same information. So now they do this internet header plus 8 bytes of next header matching to match the ICMP redirect. So I thought that maybe we somehow could know what to send to the user. So we need to know either the existing communication based on what we sent the ICMP redirect packet, or maybe even better, let's just trigger that communication. So let's assume that as an attacker, you would like to eavesdrop communication, again, from the user, from the laptop here, to the server. You know IP address of the user. You know IP address of the server, obviously. You have to be, as an attacker, on the same subnet as the user. You don't have to be on the same subnet as the server is. Actually, server should be remote server for this to work. So you don't know if the user is speaking to the server. But what can you do? Maybe you could make user to speak to the server. So you send this packet marked with 1 as a trigger packet. You could send something to the user claiming that you are the server, and user will respond to the server. So as the user responds to the server, you know something about that communication from the user to the server. So now you can send a redirect message based on that response. So your redirect message, which is number 3 here, will be based on the message number here. And message number 2 in this picture will be based on 1, which you've sent. And I will show some frames in a minute. So just remember that we focus on message number 1, which is trigger packet, claiming to be from the server to the user, then message 2 from the user to the server, and message 3, which is spoofed as it would be sent from default gateway, but attacker actually sends this message claiming to be default gateway, and this is the redirect message to the user. And then after user recognize this message and install new route in the routing table, we have man in the middle, so this yellow communication going on again. So this is like full ICMP Type5 Code1 message format, and this is the message like a datagram number 3 in our previous slide. And on the right you can see the message 2. So this is a part of the header of the message that would be sent from the user to the server in response to our message number 1. And we will focus on just a few fields here. So the source IP address of the IP datagram that will be sent from our attacker box would be default gateway IP. You need to know that. But typically, it would be the same gateway as if you are on the same subnet. You, as an attacker and user, would have the same IP address for the default gateway. Then we will just put the Type5 Code1 as the ICMP redirect to, and this destination obviously is a user. Then we will put Type5 Code1 for ICMP redirect. Checksum will be calculated automatically. And the purple one, dark purple, this is the IP address of new gateway to reach the destination. So we put the attacker IP address in there. And then next one, we embed IP header and 8 bytes of the next header of the packet number 2. So the response which was sent from user to the server. So the source IP address is user, destination IP address is remote server, and then we need to put there 8 bytes of the next header. So as you can see so far, we more or less know everything we need to construct this type of packet. But what could be the problem here? What's in this 8 bytes? So this is again the packet number 1 from remote server to the user, just a header, and packet number 2 from user response to the packet number 1 to the remote server. So this is the 8 bytes of next header for the 3 common protocols. For TCP, we would have to know source and destination port and sequence number. For UDP, we would have to know source and destination port, length, and checksum. And for ICMP, so I chose echo request and reply, which is a bit different than all other ICMP messages. We would have to know type, code, header checksum, identifier, and sequence number. So as you can see, everywhere there is some problem. So like for TCP, what would be the problem for us? Sequence number, because when we send the trigger, we put some random sequence number, and the user would respond with another random sequence number. So we don't know the sequence number. So this is like a problem number 1 for TCP. For UDP, so do we know all the time if user has the UDP port opened or not? We would have to probe this first. So that's like 1. We can, if we choose the port which is closed, the result would be only the ICMP message, which is port unreachable. So we would have to first know which port is opened, and that this communication, like the user would respond to that trigger UDP message. One good example for that would be NBT protocol. So part of, like if that is Windows, part of like shared files, it runs over port 138, and it's on Windows machines, it's almost always opened. But again, we have like length and checksum. We don't necessarily know. And for ICMP, type is known, code is known, checksum, not really, right? Because we don't know the whole contents of the packet, or do we? And then what's ID and what's sequence number for ping. So what do you think, which one of these is easiest to do? So, anyone? Okay, I'll tell you some tricks that I've learned when I was doing this research. For TCP, there is a cool trick, because if you send your TCP sync to port which is closed in the response, you get RST. And RST will set sequence number always to 0. So you know, right? You have source port because the source and destination port you control when you send the trigger. And user will send the response with sequence number 0 if you send it to the closed port. So that's one. For UDP, it depends. There are some protocols which you can know the length in advance, like NTP protocol sometimes. For some NBT messages, you can know it as well. For the checksum, I've learned that this is completely ignored by OS. So it doesn't matter. Checksum doesn't matter. For ICMP, header checksum probably doesn't matter. And let's see, because ICMP was the easiest one for me. So what about identifier and sequence number? So this is like a T-Shark or TCP dump for ICMP echo request and echo reply. So attacker would send echo request, and the user would respond with echo reply. So what you can see here. So sequence just start with 0 and will go sequential one by one, and your user will always respond with the same sequence number. And how about ID? I'm sure you're just shy and everybody sees by now. So ID is just process number in OS. So if I do ping command, I know like my process ID in this example was 41118. In hex, it's A09E, right? So you can see that ID has this trailing 0, but it's just because of the length of the field. But anyway, it means that the user who sends ICMP echo requests or ping message, this user knows, like, controls what the identifier and sequence number will be in the response. So we have it all here. And as for tests, so I didn't test this on Windows 10 or 8, just Windows 7. You can test it, I will give you the tool. You can use just any trigger. It can be based on TCP, UDP, ICMP, and the attack will just work. macOS, I couldn't make it work. I think even if I deliberately removed the ICMP redirect, that they are no longer, like they are accepted again, it didn't work, but someone just told me that it might be because of the firewall, which is built in often in macOS. I didn't test it a lot. For Linux, it was different behavior depending on the kernel. So most weird kernels were 3.6, and I don't know why, but ICMP trigger wouldn't work there, and only UDP, based on some communication that was going on, was working. But in blind, I suggest you just test it with the ICMP trigger, and it works. Last kernel I was testing that on, that was 4.6 kernel. So if you want to test your environment, you have to remember that if you are doing man in the middle, make sure that you are capable of passing this traffic through your host. So first, the IP forwarding needs to be enabled, and you need to remember that it can be a lot of traffic, so be just prepared to do so. And there are just like some memory joggers how to enable IP forwarding for different OSs. But I would like to show you the testing tool. It will be just a video. I didn't want to, mess with demo gods. So I hope this works. And this actually starts or not. Okay. So there are three machines right there. The first one is in Attacker. There are a few interfaces there, but we'll focus on the last one, so ETH4 for the victim. There are also a couple of interfaces there. And again, we will focus on the same subnet. I can show you what the kernel version is on this machine. So this is 4.6. And there are a few interfaces there, and we'll focus on ETH3, so the same subnet for attacker and user. We're checking if ICMP redirects are enabled here. And by default, every OS right now has ICMP redirects enabled. Linux has a feature which is called secure redirects, and this is something I told you about before, that Linux OS will check if the packet comes from the default gateway. So it's enabled here. And this is the remote server which will be attacked by the attacker. So the communication between the user and the server should go through the attacker box. So again, this server has a few interfaces. We use the last one, so 10.12.12.67. And just to make sure that it's not the same subnet, we'll check default gateway for our user machine or victim machine. So the default gateway is the one that ends with 252. And then it should be a trace route next, I think. Oh no, so we went to the user machine. I was typing slowly, sorry. Then we're checking what's the default gateway for remote server, so 10.12.12.67. And default gateway is 10.13.13.252. And then the trace route to see how the packet would be routed normally. And we can see there are 3 hops. The first hop is default gateway. The 254 IP address is just because there is some high availability, so 2 routers that are running in like Cisco HA. And you can see that here for the attacker, we have IP forwarding enabled. Attacker needs to have super user rights because we will be writing raw packets that need super user rights. So if you do it from Windows, also you need to have admin rights. And there's the redirect tool. This is a tool written in Golang. I choose Golang just because it can compile on most important platform. So you could use binary from Linux, from Windows. From Mac, it doesn't work yet because network stack needs to be handled differently for each operating system. But right now, it works for Linux, like here, and for Windows. So to send this redirect packet, -A will tell attacker IP address. -D is just a bit more verbose information. It's not as verbose yet. And this tool is really like proof of concept and dirty code. This was my first code ever written in Golang. So if you see it, just forgive all mistakes and not really neat code. Then -G is the default gateway, which is current gateway. -T is our target server, and -V is our victim or user. -E will just show which interface to use. So now we send in the packets. First, this is ICMP echo request, and then R is the redirect message. And we have to check if that changed anything on the user computer. Let's just check what's the route on the user machine right now. And you can see that right now this is redirected route, and it goes through 10.13.13.1, which is our attacker box. And the trace route will show one more hop. Thank you. So I think I had something more here. Yes, so there is one more feature which I coded, which is cleanup. When you put -C1, it means that it has to clean up. And it does exactly the same, but the opposite way. So now we are sending ICMP redirect from current gateway, redirecting it to the proper gateway. So it's just, right now, it's just clean. So you can see that the route is back where it should be. So that's the demo. So the summary. Attacker actually just needs to know the IP address of the gateway that the not yet compromised, but the host he wants to compromise is using to communicate with the target. So the gateway from the user to the server. And for Linux kernel 3.6, it would have to know also the ongoing UDP communication. I'm not sure, and I can't remember if I was able to make it with UDP trigger. Probably not. So this kernel is somehow, but later they fixed it. I don't know why. So it will work later. And you obviously know your target and victim IP addresses. So this is all you need to know, or attacker needs to know. Constraints. So this is one way, man in the middle, but you can overcome that doing network address translation, and you have to be, as an attacker, on the same subnet as your victim. But it's towards the remote host, and like in comparison with ARP spoofing, the first you just send 2 packets instead of constantly poisoning ARP routing table. And if your target is remote machine, you will only redirect traffic to that machine. Whereas if you used ARP spoofing for the same, you would have to redirect all the traffic going to the gateway. So all the traffic from your victim machine would have to go through your hosts. So this one is more stealthy and very targeted. So it's not a bug, it's a feature, right? It's easy to just get rid of that feature. You can just disable it on the OS level, and all OSs have features to disable ICMP redirects. And there is really, like, having this 10 years of being network person experience, I can tell you that there is no reason you would like to have ICMP redirects working right now. Even for like a beginner network admin, it's just a headache because they don't know why the route suddenly changed. So you don't need ICMP redirect, just disable it everywhere. If you are like domain admin, then disable it on all hosts. That's it, and then you're safe. And if you are network admin and you would still have to do something for the hosts that are not protected, there are spoofing is just enough. Anti-spoofing mechanisms are just enough to get rid of this problem, but it has to be on a switch access port level. So it has to be on this local subnet. It can't be any ACL, which is just on the router. It wouldn't work. So it has to be on the port level. And I'm mentioning Cisco because I have most background in Cisco. I don't want to say that it's the best. Probably other vendors have protection mechanism as well. So now there are just few references. RFC I've used to do this research. The first link from the links section is also about ICMP redirects attacks. So last one, so there are some Cisco hardening guides. This is the favorite one. These are all or most of the kernel commits that changed ICMP redirect message handling. And the last link is just a summary of the changes. So please do contact me if you have any questions. I will respond to emails. I'm happy to engage. I don't have this tool available publicly yet, but I will do that. But still, I don't promise that it will be a very elegant tool because I'm not a programmer, so the code is just like, you know, me coding. And that's all. Any questions? There's a question.
Hello. Just to understand, the first schema, the attack didn't work because the victim had to instantiate the communication and just answer the ECMP with IP address of the router. That's it. There is two changes that make the first attack not work in the most recent kernel. That's it.
I'll show you. So before, you could just send any ICMP redirect message, and it wasn't matched at all with current communication from the user workstation. So you could really blindly send ICMP redirect for particular destination, and OS would install this new route. Right now, it will first check if there was a corresponding packet which should cause or could cause this ICMP redirect message to come. So it should be there should be first a communication going on between user and target. If there's no, then the redirect will be just discarded. And then next step would be the ICMP redirect should come from default gateway, so IP source address of the redirect packet, and that would be, oh, actually, this first green, this first blue header. It should come from default gateway, and also it should come from the proper interface. And the third thing that was changed, that they now actually do check if there was corresponding communication, and that communication is actually checked if this is the right communication. So you have to know all the fields here. Okay, thank you.
Hello, Erwan Broker from Cerema. You talk about ARP spoofing. At the end, yes. And thank you for explaining the difference of the two different attacks. My question is about this attack, ARP spoofing. It is a very old attack with 20, maybe 30 years old attack, and it is still not corrected, even with firewalls. I use it with firewall, it works. And what is your point of view why it is not corrected?
Okay, so ARP spoofing is also attack which is performed on the local subnet. So firewall won't protect against it typically if you don't have, so ARP protocol is kind of layer 2, layer 3 protocol, which means that you cannot protect against this attack using IP firewall. So for protocols IP, TCP, UDP, and above on the OC stack. So you would have to have a firewall which is aware of layer 2, so Ethernet in this case. And also it would have to be on a switch port level actually, because this ARP spoofing attack is going from one, let's say one workstation to another, and the path that this traffic is taking is going from one workstation to the switch port, and then from this switch port on this one switch to the next switch port and to the other workstation. So it's not going through firewall, it's not going through any ACL unless you have ACL, so access list, applied to the switch port. And some vendors, including Cisco, which I know the best, has protections against ARP spoofing, so you just need to configure the ARP spoofing protection on every single port in your network. So every device that has like wire connected to your switch needs to have this, on the switch port level from the switch perspective, needs to have this protection enabled. And some companies do that, and you can't ARP spoof. Some don't. I don't know why. It's a bit overhead because you have to have it on every single port. And if you just have this little switch, which is not high-end switch, there is no way to protect against that. So I guess that's the answer.
You talk about IPv4. In IPv6, ICMP is responsible of more things. If I remember, it replaces more or less IRP. Do you made any experiment with ICMP v6?
With this research, I did not. I don't have a lot of exposure to IPv6 right now. I can add that to my R&D queue.
So thank you for your talk. So you explained that this protocol is still implemented in recent distribution, in recent Linux kernel in Windows. But what is the default value for the configuration settings you show with sysctl and in Windows the registry value? Because I think that on Ubuntu the default value is 0. I just checked on Arch Linux, it's also 0. But is it something we need to be worried when we install a new system, or is it something that is well configured by default?
So I'm not sure how much you could see this attack in a wild. It's also very difficult to detect because if you would have to collect pickups on all interfaces to know that you were, victim of this kind of attack. So you saw the constraints that the attacker had. They have to be on the same subnet as you are. So if you don't trust the subnet you're in, you can be worried about this attack. And actually, you can be really very worried because they can even do like two-way man in the middle. They could sniff your SSL traffic, and you probably know that you wouldn't trust some weird certificate in your browser, but like typical regular user would maybe you wouldn't know that. So they could also like eavesdrop SSL traffic and decrypt that. So if it's just at home, as long as your network is not compromised, you don't have to really worry. And just like, you know, for Windows, you can just do this rec file for your, I don't know, family. They just click it and done. So, I don't know, does it answer your question?
Any other questions?
Maybe I didn't catch up properly, so we can talk afterwards.
Well, thank you.
Thank you.